Welcome to the deep dive. You know, whenever we talk about building things, whether it's a physical structure like a bridge or something complex like software, the really impactful choices, they happen way before anyone lays down steel or writes code. I actually wanted to kick things off with a quote. R. Buckminster Fuller. He said, "We are called to be architects of the future, not its victims."
Hmm.
And that spirit, that deliberate design, is exactly why we're doing this deep dive into software architecture's foundations. Our mission today is pretty straightforward. Give you the essential shortcut to understanding architecture's core concepts, really from a software engineering angle. You should walk away knowing what architecture truly is, and, crucially, how it's your main lever for getting quality right.
Yeah, and what's really interesting is how the source material right away frames architecture as this critical bridge.
A bridge, how so?
Well, it connects those abstract business goals, like we need speed or it has to
Mm.
be secure,
Yeah.
connects those to the actual concrete system you end up building. And look, the good news is this complexity, it's tameable. We've got techniques, design, analysis, documentation to manage it.
Right. So if it's this essential bridge, we have to start with the big question. What is software architecture, really? Because you ask 10 different people.
You get 10 different answers, usually
Yeah.
something about early decisions or important components, that kind of thing.
Exactly.
And the definition you use here cuts through that. It's focused on engineering leverage. It says architecture is, and I'm quoting here, the set of structures needed to reason about the system.
Okay.
These structures comprise software elements, relations among them, and properties of both.
All right, let me push back a little. If everyone talks about the big, important decisions, why focus on structures? Isn't documenting the decisions enough?
It's about what's more reliable for analysis.
Mm.
A decision happens, well, it's an event in time. Sometimes you only know later if it was really major.
Mm.
But structures, the patterns of elements, how they relate those, are always there. You can identify them, analyze them. So architecture, in this view, it's fundamentally about creating reasoning-enabling structures. Tools for analysis, really.
And the point of that reasoning, that analysis,
Yeah.
it's not just academic, right?
Well, absolutely not.
It has to tie back to something a stakeholder actually cares about. Like, functionality, sure, but also modifiability, performance, how it handles faults.
Precisely. And that leads straight to a super important point. Architecture has to be an abstraction,
An abstraction meaning.
meaning to manage all that complexity, you deliberately leave out the private stuff, the internal implementation details of some component. You focus only on the public interfaces, how elements interact.
Ah,
That's what lets you reason about the whole system without getting totally lost in the weeds of the code.
that helps clarify the whole architecture versus design thing, too.
Yeah.
So architecture is design.
Yes, it is design.
But it's that high-level design setting the abstraction.
Yeah.
You define the key structures, and then tons of smaller decisions are left for, downstream designers and implementers.
Exactly. And two things are really vital to grasp here. First, every single system has an architecture.
Right, because it has elements and relations, even if nobody wrote it down.
Correct. Even if it's accidental or just emerged.
Yeah,
And second, just because it exists doesn't mean it's a good architecture.
good point.
Fitness for purpose is everything. You build a system meant to last 5 years using an architecture designed for a quick prototype.
Yeah.
That's a bad fit. Mismatch.
That's a really sharp distinction. Okay, so let's zoom out a bit. Software architecture doesn't live in isolation, right? There
Sure.
are bigger planning contexts that impose constraints. You mentioned system architecture and enterprise architecture.
Yeah, exactly. If we pull back,
Mhm.
system architecture is the widest view. It looks at the whole thing, hardware, software, and the people involved. The system architect figures out how to map functionality onto the physical resources, which processors run what, the network setup, physical locations maybe. Reasoning there involves things like power draw, weight, physical size, stuff that impacts the physical world.
So that defines the physical box the software has to fit in, essentially. What about enterprise architecture, then? If system architecture handles the physical layout, what's left for EA? Isn't that just like org charts?
No, it's much more strategic than that. Enterprise architecture deals with the organization's structure and behavior, its core processes, how information flows, how people are organized.
I see.
It doesn't design the software itself, but it sets critical constraints. Things like a mandatory global data model all systems have to use, or standards for databases or operating systems. It's about making sure all the software aligns with the overall business goals and processes.
Okay, so the takeaway is pretty clear then. Both system and enterprise architecture create the environment, the sort of non-negotiable boundaries that the software architecture has to respect.
Absolutely. You can have the most elegant software design, but if it breaks the enterprise data model or needs more power than the system architect allocated, it's failed its mission.
Got it. Let's pivot back to the core, the structures themselves. If architecture is structures, the book groups them into three big categories: for design, documentation, and, crucially, analysis.
Right. And I really like the analogy they use. Think about a building, like a house.
Okay.
You've got different specialists looking at it. A neurologist cares about the nervous system, a plumber cares about pipes, a framer cares about the studs and joists. They all have valid, essential views of the same thing.
But no single view tells the whole story. The plumber doesn't care much about the framing details, and vice versa.
Exactly. You need these different perspectives for different kinds of reasoning.
Makes sense. So let's tackle the first category, like the framer's view, the static parts.
That first category is module structures.
Yeah.
This is the static view, looking at how the system is broken down into implementation units, the code, the data files.
Static, meaning how it's organized when it's not running.
Precisely. And because of that, these structures are primarily used for reasoning about modifiability. How easy is it to change something? Where do changes ripple?
And there are different kinds of module structures.
Yes. For instance, the decomposition structure. That shows how bigger modules are broken down into smaller submodules, recursively. This often directly influences how you organize the development team and assign work.
Okay, that makes sense for project management. What else?
A really important one is the uses structure. This shows which modules depend on others, like module A uses module B, meaning A needs B to be present and correct to work properly.
Ah, dependency tracking.
Right. And that's vital for things like creating functional subsets for release or planning incremental development. You know exactly what other pieces need to be ready. We also have the layer structure. Think of layers like abstract virtual machines. This view is key for analyzing portability. Can we swap out a lower layer?
Okay, so that's the static view, focused on code organization and modifiability. What about when the system is actually running? That's the second category, right? Component and connector, or C&C.
Exactly. CNC structures are all about the runtime view. How do elements interact while the system is executing to get the job done?
So the elements are different here, not just code modules.
Right. The elements are runtime things. Components like active services, clients, processes, and connectors. The pathways for communication, like procedure calls, network sockets, message queues, pipes.
And this dynamic view lets you reason about different qualities.
Absolutely. This is where you analyze runtime quality attributes. Things like performance, how fast does it respond? Security, where are the vulnerabilities in communication? Availability, what happens if a component fails?
Can you give an example?
Sure. Think about the concurrency structure. It maps components to logical threads. This helps you spot where you can parallelize work, but also where you might run into resource contention, like multiple threads trying to access the same data,
Right.
causing bottlenecks. Or the service structure. Components are services talking via messages. Great for analyzing robustness. What if a service is slow or down? And interoperability.
And these runtime behaviors, you often can't easily see them just by looking at the static code structure, the modules.
You really can't reliably infer them. That's why this CNC view is essential.
Which brings us to the third major category, allocation structures. You called this the mapping view earlier. Mapping what to what?
Allocation structures bridge the gap between the software world and the non-software world. They map software elements onto things like hardware, the file system, or even development teams.
Ah, okay, so connecting software to its environment.
Precisely.
Yeah.
The deployment structure is probably the one people think of most often. It shows how runtime elements, usually processes or containers, are allocated to hardware elements, servers, processors, devices.
And that's crucial for distributed systems, obviously.
Oh, absolutely. You use it to reason about performance bottlenecks due to network latency, security zones, reliability if a server goes down, and just basic deployability. Where does this thing actually run?
You also mentioned mapping to teams. That sounds interesting.
Yeah, that's the work assignment structure. It maps the static modules, the units of code, onto the organizational units or teams responsible for building and maintaining them.
And that's an architectural decision, not just project management.
It has huge architectural implications. Think about Conway's Law. The system structure mirrors the communication structure of the organization. The book points to Amazon dedicating a single team per microservice.
Right, the two-pizza team idea.
Exactly. That decision profoundly shapes communication overhead, expertise boundaries, how independently things can evolve. Your allocation structures define the physical and the human context the system operates within.
Wow. Okay, so we have these three distinct categories: module static, CNC runtime, and allocation mapping. How do they relate to each other? Are they totally separate?
Not at all. They're definitely not independent. The mapping between elements across these views is typically many-to-many.
Meaning?
We'll take one module from your static module structure. At runtime, in the CNC view, that single module might be running as multiple instances, maybe replicated components for load balancing or resilience.
Can you give a simple example?
Sure, think of a basic client-server system. In your module structure, you might just have two modules, client code and server code. Pretty simple static view.
Okay.
But now imagine 10 users running the client simultaneously, all connecting to that one server instance. In your runtime CNC structure, you actually have 11 interacting components, 10 client components and one server component.
Ah, I see. One module, multiple runtime components.
Exactly. The module structure helps you figure out if you can change the server code easily. The CNC structure helps you figure out how fast that server responds when 10 clients hit it at once. Different views, different questions.
That clarifies things a lot. So with all these structures in mind, what does the source material say about achieving a good architecture? We know it's about fitness for purpose.
Right. A throwaway prototype doesn't need the same robustness as a banking system,
So what are the practical recommendations?
process-wise.
Key process recommendations include, first, aiming for conceptual integrity. That usually means having a single chief architect or a small, tightly knit team lead to keep the vision coherent. Otherwise, you get architecture by committee, which rarely works well.
Okay.
Second, and this is crucial, the architecture must be driven by a prioritized list of quality attribute requirements.
Not functional requirements.
Functionality is table stakes. Everyone assumes it works. The hard part, the part architecture really tackles, is achieving the desired levels of performance, security, modifiability, resilience, and so on. Those qualities need to be explicit and prioritized.
And you need to check if you're hitting those targets early.
Yeah.
Right? Absolutely. Evaluate the architecture early and often. That's when changes are cheapest and have the biggest impact. And design it to allow for incremental development. Build a skeleton first, maybe, that proves out the core communication paths before you flesh out all the features.
Makes sense. What about structural rules of thumb, concrete design advice?
On the structural side, good old information hiding and separation of concerns are paramount for modules. Encapsulate the things you expect to change behind stable interfaces.
Classic Parnas.
Exactly. Also, don't try to invent solutions for common problems from scratch. Leverage well-known architectural patterns and tactics. They exist because they're proven ways to achieve specific quality attributes.
So use patterns for performance, patterns for security, etc.
Right. And remember that module-to-component mapping isn't one-to-one. Don't assume your code structure directly mirrors your runtime structure. Finally, a very practical tip for today. Make sure your runtime processes can be easily moved between physical processors. That supports virtualization, cloud deployment, scaling. Very important.
That was a fantastic tour through the fundamentals in Chapter 1. Let me try to recap the absolute core idea for you, the listener. Software architecture isn't just some diagrams, it's the deliberate selection of a set of structures.
Module, CNC, allocation.
Chosen specifically because those structures allow you to reason effectively about the system's most critical quality attributes long before it's fully built.
That's the heart of it. These structures are your primary engineering leverage points. They let you analyze, predict, and control qualities like performance or modifiability in a way that just looking at lines of code never could.
Okay, so here's a final thought to leave you with, building on this idea of needing structures for reasoning.
Yep.
If you have a really simple system, say non-distributed, single process, maybe just for internal use, then maybe a simple decomposition structure and one basic CNC view are all you really need. Documenting a complex deployment structure might be overkill.
Could be.
So the question becomes, when does the cost, the effort of defining, documenting, and maintaining a specific architectural view start to outweigh the benefit you get from the reasoning it enables? Finding that sweet spot, that balance, well, maybe that's the real art of software architecture. Something to think about for your next project. Thank you for joining us for this deep dive. We'll catch you next time.